Thank you very much. I would like to start by telling you two things about you all here, about us all here. We are all at the same time, from a chemist's perspective, absolutely remarkable and unique, whilst being at the same time completely ordinary. Okay? You see, all of us here are about 60% oxygen, 20% carbon, and 5% hydrogen. So that means that all of us have more or less the same composition as this piece of wood. However, what's remarkable about us is the way that these elements of carbon, hydrogen, oxygen combine to form these wonderful, complex molecules that enable us to do remarkable things. For example, each and every one of you now is sitting there and you have two black holes in your face. And those black holes are very good at absorbing photons of light that reflect off me, that go towards you, they enter your black holes, they go to the back of your eye, and the intensity of these photons and the wavelength that they have give you a picture. Your ears are tuned to hear slight changes in the pressure waves that are radiating in this room. Your skin can feel temperature change very accurately. All these are due to molecules that you have that allow you the uniqueness of being able to observe the universe, to actually be conscious of your own existence. Your molecules make you intelligent of your own molecules. That's why you're amazing. How do we get this complexity? How is it possible? To understand that, we have to understand something about the chemistry of this planet, and in particular, the chemistry of carbon. Now, can I maybe ask, are there any volunteers, any young people here who would like to come and help me with a, yes, come up onto the stage. Yeah, come, welcome up, quickly. Off you come. Yes, do come. All right, come in front of me, please. Thank you very much. Turn and face the audience. Okay, that's enough, I think. Okay, yeah, you can come along as well. Right, let's look at your mums and dads as you face the audience in one line, a nice line here. Okay, face the audience, give a big wave. Okay, now, what I want you to do is you to all pretend to be an atom of carbon. I want you to do the same. For a moment, forget that you are Pedro or Michael, and imagine you're just a single atom of carbon, which isn't, of course, too difficult because actually we're many, many, many billions and billions of atoms of carbon. But you're just one atom of carbon. Okay, so our atoms of carbon, all of us here, your beginnings, you are many, many billions of years old. And you were created, we were all created as atoms of carbon here, in a star. In the center of the star, bigger than our own, the sun, there's huge temperatures and pressures. So I want our atoms of carbon to turn around on the spot very quickly. Can you turn around like that? Spin around. All of you to spin around. Okay? So keep spinning, keep spinning, keep spinning. This is our atoms of carbon at the beginning. Very high temperature, very high pressure. They're spinning around many, many, many billions of times every single second. If we could see, we would see a bright blue-white light, extremely intense. And there you'll be spinning, keep spinning, kids. We'll be spinning and spinning and spinning so fast for many, many, many hundreds of millions of years until all of a sudden, boom! And kids, as our atoms of carbon, we're traveling through the galaxy, like me, quick. Traveling almost at the speed of light through the galaxies, at the speed of light, traveling as your atoms of carbon, and they keep traveling and traveling around until eventually they come across a gravitational pull. Okay, kids, follow me. A gravitational pull, we're going to run around in a circle. A gravitational pull that begins to cause these atoms of carbon to get closer and closer, come to me, closer and closer to each other, and they form a lump, as in our planet Earth. And there, these atoms of carbon, you are most likely to combine with oxygen and form covalent bonds with oxygen, indeed, young man, and you'll become most likely a carbonate. Calcium carbonate. You'll probably salt out in the oceans as calcium carbonate, like the white cliffs of Dover in England. And there they would be, with one atom of oxygen, another atom of oxygen, another atom of oxygen, around them, underneath the surface. And there they would stay. Underneath the surface, where it would be dark and 8 degrees Celsius every day. There would be no change. They would sit there patiently for a year, for 1,000 years, for millions of years. No movement, no excitement. They began by spinning around in the center of the star. They exploded across the universe, and now they are all alone, surrounded by oxygen. It's dark and it's cold, and nothing ever happens. Until one happy day, Ivan comes to work with his pickaxe. And there he goes to work exactly where our atoms of carbon live. He's mining here. He's mining the calcium carbonate. So one day, as you're under, like every other day, we're there in the dark and the cold, you hear a boom. All of a sudden, bang. The earth opens. You feel the sunshine for the first time in hundreds of millions of years. You look and you see the blue sky and the white clouds. There, Ivan takes you into his wheelbarrow and he takes you over to the kiln. And he throws you in where there's an oven with temperatures of about 1,200 degrees. Enough energy to make your molecules begin to wobble and wiggle. Wobble and wiggle, guys. Wobble and wiggle, wobble and wiggle, wobble and wiggle as more and more heat energy gets into us until all of a sudden we can't resist any longer and bang! We release our calcium and oxygen as lime. And the carbon, our atoms of carbon, we change into a new molecule of carbon dioxide. And as carbon dioxide, okay, freely dance, let's dance. If you freely move around, the carbon dioxide, freely move around, kids. The carbon dioxide floats around the Earth, our planet. As an average, 7 years, it crosses our whole planet. We go over the mountains near Kazakhstan. We travel over the forests of Europe. We have this amazing life back to us as a molecule of carbon dioxide. Can you see why carbon likes to be carbon dioxide? Our next door neighbors, Venus and Mars, 95% of the atmosphere is carbon dioxide. Carbon loves oxygen, and it loves being carbon dioxide because it's free. If you're hot, kids, keep moving around. If we're hot, we can go for a swim. Do you like swimming? We can go into the water. We become a carbonic acid for a small amount of time. And then once again, we're pushed out of the equilibrium as a molecule of carbon dioxide back into the air. Maybe a bird comes along and breathes us in. You go into the bird, into its lungs, into its bloodstream. Hemoglobin tries to get you, but it can't because you're carbon dioxide. You flow through until the bird eventually breathes you out. Maybe over a vineyard, kids. And there, we have our destiny. Hey, you're very clever, young man. There's a job at in my research group for you. Yes, the carbon dioxide, if the conditions of pressure are just right, the carbon dioxide is pushed against the leaves of the vine. And there, it combines with water that comes up through the Earth's surface. And in a miraculous moment of sunshine, as this young man says, we convert ourselves from carbon dioxide into a molecule of glucose. Glucose. This is the miracle of our planet. That we, and when I say we, I mean maybe only we, of all that we understand about any planetary system in our universe, we are the only planet that can change carbon dioxide and change it into glucose. What's the difference? Well, for me, carbon dioxide, for me, and these are the miracle workers in action, for me, carbon dioxide is like an old man, a happy old man. But he's reached his maximum. He's reached his, or at least he's in his energy minimum. He's happy. He has nothing to prove. He has nobody to show anything further to. He's happy as himself. Water is this wonderful old woman who's also happy with herself. She does not want to change. But photosynthesis takes these two old, energy-less molecules, and it stores the energy, the sun, the solar energy, in a new chemical form of glucose, where glucose for me is like these young boys who are on stage here, full of energy, full of passion, wanting to show the earth what they can do. And oxygen, a beautiful molecule, like a wonderful, beautiful young lady, irresistible to all. Photosynthesis traps the energy from the sun and holds it in chemical energy that enables us to be here. This young man here, glucose molecules, that is the beginning of all organic chemistry, of which we are perhaps the most amazing result of its continued development on this planet. So that's how glucose got here. Here, I've got this is sucrose, it's another sugar. It's two molecules of glucose together. And we know this white chemical rather well. If I put it into my mouth, I can immediately feel the effects it has on me. It begins to dissolve, and I can feel the energy that it's supplying to me. My brain is already saying, thank you, Michael. I needed a bit of a boost. That's enough. So, sugar is where we start, but it's not where it finishes. When plants and trees have made too much glucose, what do? Well, what happens is that individual molecules of glucose begin to link up into long, huge molecules, a polymer, where individual glucose molecules line up next to one another into a chain like this. We call that natural polymer cellulose. And what I want to talk about today is the chemistry of these huge, big molecules. We're going to talk big, ladies and gentlemen, big and complex. Why? What does this bigness, what does this size increase mean? Well, let me give you a metaphor. I think it's very similar to the success of previous warlike nations, like the Vikings and the Romans. Watch this. Notice the shield wall, how it protects the Vikings from the attack from the Anglo-Saxons. Or now the Romans running into battle, far fewer Romans than enemy. What do they use? A shield wall. This is the regularity of complexity. It's the organizations of shields that give the Romans and the Vikings their power. And it's the same with chemicals and polymers. It's the organization of single units into a long shield wall that give it the properties of strength and durability and all sorts of physical properties that we can use in our modern day life. Allow me to tell you the story of how this chemistry developed and how human innovation made it happen. So cellulose is the basis of, well, it's a natural polymer that we use, for example, in our clothing. So this is a cotton t-shirt, and that cotton is cellulose fibers linked together. And we can plait these fibers together to make a material that we can wear. It has a use. Now, about 180 years ago, in Switzerland, there was a Swiss chemist who began to play chemically with such a natural polymer as cellulose. What he was doing was he was experimenting what happens if I put in lots of extra atoms of oxygen and nitrogen into this network of cellulose fibers, which are, of course, carbon, hydrogen, and oxygen. And this is a result. And this result began polymer chemistry. It was an accident. It happened because he spilled some acids in his laboratory and he mopped it up with a cotton cloth, which when dried, did the following. Okay, can we flip to the, yes, good, fantastic. Okay, so here I have some cotton, and I've done exactly the same as what Schoenbein did all those years ago. Okay, I treated it with concentrated sulfuric acid and nitric acid, and you can see if I just add a little bit of energy at the beginning, then what we get is a nice flame. Try again. Are you watching? I want you to notice two things: the speed and also the products. If you notice, it goes very, very quickly, and there's not much that's left over with. It burns almost without, and this is what's important, without smoke. Now, in his laboratory, Schoenbein, which by the way is German for beautiful leg, Schoenbein had an idea. He observed what you've just observed, and then he thought how he could apply it. And what he did was he contacted the armed forces. You see, at the time, if we can go back to the thank you. At the time, a lot of new artillery and innovation in the armed forces was based on gunpowder. Now, gunpowder, when it's lit, produces a lot of smoke. That's bad in two ways, really. First of all, imagine that you're on the battlefield and you're hiding somewhere with your gun. As soon as you fire your rifle, a puff of smoke, your position is revealed to everybody. Or, if you're in a ship with lots of guns, with lots of cannon guns on deck, you start firing with your gunpowder, what happens? The deck very quickly is full of smoke. You can't see, you're not as effective. So when Schoenbein introduced gun cotton, this chemically improved natural polymer, well, that was a huge advance. And it made a really big competitive advantage to those forces using it in their wars. What's the result of this? The result is that chemists discovered that through chemistry on natural polymers, there is the potential for economic success. Now I'm going to fast forward about 20 years. And I want you to imagine you're in a gentleman's club, a well-to-do person with some leisure on your time. What do they do in the 19th century? Well, they would play often billiards. And billiard balls, does anybody know from what material billiard balls were made? What, is it you again? You're a genius, young man. Yes, you really are clever. Yes, elephant's tusks. Ivory is the name of the material. So ivory was used to make the billiard balls that gentlemen would play billiards with. Now, of course, that wasn't sustainable. And very quickly, the gentlemen in their club decided that it's not good enough. There has to be a change. We have to change the material from which it's made. So what did they do? They put up a $10,000 prize. And $10,000 in those days was a lot of money. It was the equivalent of today's X prize, okay? Millions of dollars. If you come up with a solution of how to replace billiard balls from ivory. Sorry? Yes, indeed. Well, exactly that. There was a clever man called, is it Henry Wyatt, I think? And he decided to use polymers. He went back to the original work on gun cotton, that's the nitration of cellulose, and he did some more chemistry with it. And what he produced when he reacted it with camphor is a new polymer that he called celluloid. You might have heard of celluloid. Afterwards, many things were made of celluloid, like buckets, for example. Now, celluloid is based on cellulose with a bit of chemistry involved, and the result is, or was, the first thermoplastic. That means it's a polymer material that you can make, then you heat up to melt it, and then you can pour it into any form you want, for example, the form of a bucket, or a bucket handle, or this plastic container, or indeed this piece of plastic, whatever you want, you pour it into the mold, and it forms to that mold. An incredible innovation step. Just imagine the possibilities available to the chemists at the time. And of course, he decided to mold these balls, the billiard balls, and he won his $10,000 prize. So, what we have now is this gaining realization amongst scientists that through their research into these huge molecules, polymers, they could provide solutions that work, that serve a purpose, that can lead to an increase in the standard of living or bring an economic success. Let's skip a bit further now to about 1938, 39. And what I want to talk about is a different type of polymer. Now, it's not just sugar that nature polymerizes. It also polymerizes proteins. Okay? Now, proteins are amino acids. Have you heard of them? Okay, an amino acid, there's a central carbon, and on one side you've got an amine group, that's a nitrogen with 2 hydrogens, and on the other side you've got a carboxylic acid group. That's a carbon with 2 oxygens and a hydrogen. And these amino acids, they can interact with one another because NH2 loves COOH. And they react, they interact, they have a reaction, they release a molecule of water, and they form what's called a peptide link, a bond between amino acids. Now, this process can continue down the chain. Indeed, you're doing it now, as we speak. You're converting the food that you ate at lunch into amino acids. And those amino acids are reacting with one another, making chains of amino acids, which are determined, the order of that chain is determined by your DNA, and that's producing the proteins that you're using now to grow kids. And all animals do that. And one polypeptide that's amazing is this. Silk, made by the silkworm. Now, silk is a wonderful natural polymer, polypeptide. And from silk, we can make these beautiful pieces of material. Maybe I can make myself a nice dress. What do you think? And the advantage of the silk is, first of all, it's very light, so it feels very nice on your body. It's very soft, and it's very, very strong. And that strength and lightness and stability makes silk not just the ideal material for dresses, but also the ideal material for parachutes. Now, if you imagine now it's 1938, and in the West, Britain and America are planning an invasion of France, which is held by the Germans. And what they need is a lot of parachutes. The problem is that parachutes are made from silk. And silk is not equally distributed amongst the countries of the planet. It's concentrated in the Far East, where the silkworms make it. So there was a problem. We didn't have enough silk to make enough parachutes. That's an economic problem. And who came up with the answer? Of course, a chemist. And that chemist was called Wallace Carothers. And what he did, I'm going to show you. It was genius. So he's got the following problem. He needs to find a way how to synthesize a polymer, a polypeptide, or something similar, which has similar properties to silk. He understands the chemistry of silk. He knows it's these carboxylic acid groups, amino groups. They come together, they kick out a molecule of water, and they form a peptide bond. His challenge was, can he replicate this with cheap chemicals that he can get from, let's say, crude oil? And this led to the following reaction. Okay. What I've got here is actually something I made in Kazakhstan yesterday evening. So a really big thank you to the university at Nur Sultan. And I've got two chemicals, which is what Carothers used. He had what's a hexaamine. And this compound is a water solution of molecules that contain 6 atoms of carbon in a chain, and at the end of the chain are two groups of NH2, amine groups at the end, okay? So I'm just going to put this into the wine glass. I hope you can see this nicely. I'm going to put it in the wine glass here. I've got a bit of food coloring in there, so when I pour this in, you should see a bit of a color change. Okay, so that's the water solution. And then the other solution he had was, I'm going to put a bit more actually in. Why not? Let's do this on a big scale, or a bigger scale. Okay, I'm going to add a bit more. Okay, so here we have our water solution. It looks like brandy, but it's not. And here I have a cyclohexane solution of an acid called adipic acid. And this also has 6 atoms of carbon in a chain. And at the end of the chains, you have 2 carbon COOH groups. And what I'm going to do is I'm going to carefully pour this chemical on the top. Now, can you see that it's forming 2 layers? Do you see that? Say yes, Michael, if you do. Thank you very much. You can see, okay, there you've got the 2 layers nicely on the camera. The bottom layer is the water. I'm just going to put this up here for now. So at the bottom, we've got or I can put it here. At the bottom, we've got a bottom layer of water. In the water, if you remember, there's the hexadiamine. So you've got 6 atoms of carbon in a chain, and an NH2, NH2. And in the top layer, we have cyclohexane, and at the ends of the 6 atoms of carbon are carboxylic acid groups, COOH. And what happens in the interface between the 2 layers is a reaction, a polymerization, where one molecule takes the hand of the next, that takes the hand of the next, that takes the hand of the next, and you get a big, long chain of a polymer molecule. And this is exactly what Carothers did. And to his amazement, when he looked inside his reaction pot, he picked up the growing polymer, like I'm doing. He literally picked up the polymer and began to take it out of the glass. And to his amazement, he realized that he had some success, that his chemical genius had formed a new polymer material unknown previously to the planet. He was successful in mimicking silk with this new polymer. And just look how much material can be made from this. And the strength of this material is extremely tough. I'm a big man, and I can't rip it apart. Even stronger than silk. And you can get lots and lots and lots of this new molecule from the same reaction pot. Carothers had solved the problem and came with a solution. And that solution was the first synthetic polymer, nylon. Nylon 6,6, as it's called. Okay, can we go back to the presentation, please? So Wallace Carothers had developed nylon, and as I said, this form of nylon is nylon 6,6, which means you have in one unit 6 atoms of carbon, a peptide link, another 6 atoms of carbon, peptide link, another 6 atoms of carbon, peptide link, and on and on and on and on and on. What he discovered was this polymer has certain properties. This polymer is strong, but soft and light, like silk, ideal for ladies' stockings, or indeed parachutes. But then he had a moment of genius. He thought, what happens if I change the number of carbon atoms in each monomer unit? So he did the reaction where he got a polymer with 6 atoms of carbon, peptide link, 10 atoms of carbon, peptide link, 6 atoms of carbon, peptide link, 10 atoms of carbon, 610, 610, 610, 610. And the result was a polymer that was more robust and stronger, ideal for toothbrushes, for example. So Carothers not only discovered the first synthetic polymer, but he understood that we can do chemistry here. Just by changing what's in the repeating unit, we get different properties. It opened up the doors to a whole new era, an era that we're living in now. It's the age of the polymer. If you look around you, so much of what we wear, sit on, look at are polymer materials. And the principles are the same. What changes is the unit between the linking components. For example, if we change the between the linking units, if we put in these circular, these ring-like phenyl, what they're called phenyl groups, benzene rings, you asked about benzene. These benzene rings repeating in the polymer system, what we get is a completely different type of polymer that we see here. What's the name of this? Okay, and any other name do you know of? Polystyrene. Yes, it's polystyrene, because between the linking units are molecules of styrene. So this is polystyrene, and This is a polymer which is really good. It's very stable. In fact, it's so stable, it's a bit of a problem. It hangs around for a long, long time as well in our environment. But what it can do, it's very good at encapsulating big quantities of air. And so it's perfect as an insulator. So we use it, for example, if we go to the restaurant and we want to take our food back home, we use it to keep the food warm. Or we use it to insulate our houses. But as I said, there's a problem that because it's so stable, it's a wonderful property, but also a property that introduces new challenges for us. What to do with the waste? Now, as a chemist, I've, of course, got a solution, and that solution is my coffee mug. I've got a special coffee mug, kids. It's a coffee mug that's very good at getting rid of polystyrene. So all I've got to do is put the polystyrene in my coffee mug, and, well, the coffee mug can take, well, lots of polystyrene in there, really. And, in fact, you know, quite a lot. There's almost a meter now gone into this coffee mug. So as I said, it's a special coffee mug which allows me to have a bottomless store of polystyrene. If that's not enough, I've got some more here, of course. And I can keep doing this with the polystyrene, as it's a special mug. There's no magic trick. There's nothing below it, of course. This mug can just keep on taking more and more and more and more and more polystyrene. Now, if anybody can tell me how this is done, I'm sure the young man... Yes, sir. Okay. What's your name? Sorry? Ansar. Well, Ansar, you are a genius. Yes, my magic coffee mug, unfortunately, is not magic. It's just containing acetone. And acetone is a solvent that can dissolve polystyrene. And, of course, as the polystyrene polymer dissolves, then it releases the air that it's encapsulated. And, of course, ultimately, this material is about 96% air and only 4% polystyrene. And, of course, if I dissolve this polystyrene, it's no longer really a waste. I can take that polystyrene liquid and I can form other useful things than polystyrene, such as thin films, which I do in my laboratory, for example, with new molecules that have the property of luminescence. So polymers are full of opportunity. They're full of promise. We live in their age, and all it needs are clever young people to see what they can do with polymers. What else can we achieve? And this is where the story comes to you and what you can do with the magic of chemistry and our understanding how to synthesize the biggest molecules in our universe, which are polymers. Oh, there's a clue. I've got one last polymer for you. Here it is. Now, this is sodium polyacrylate. Okay, you can see there's a small amount of white powder there. It's a small amount of polymer. And what I'm going to do, I'm going to pour myself a glass of water. Yes. I'm going to pour myself a glass of water, and I'm going to show you something. So I'm going to show you a property that this polymer has, and then I want you to think about how you can use this property. Because if you're a budding chemist, a budding scientist, and you observe something in the laboratory that you're working on, that's not enough. You've got to think as well, how can I use this? So here's the polymer. Here's some water. I pour the water in to the polymer. And then I just wait a little moment, and all of a sudden, well, yes, the water has seemed to disappear. In fact, if I turn it upside down, nothing escapes. What's happened? No, it hasn't reacted. He's right again. It's absorbed the water. In fact, this polymer is a super absorbent. I can pour some more water in here, perhaps, and see what happens. I can get a bit more water in there, give it a bit of a stir. the water will once again be absorbed by this wonderful polymer. And I could keep going, really. My glass is not big enough. I could stick in there another litre or 2 litres of water. The same thing would happen. This polymer would just keep on growing as it absorbed more and more of the water. In fact, this polymer can absorb 300 times its own molecular weight in water, an enormous volume. So, that's sodium polyacrylate. Who can tell me, how can we use this property? The man say, obviously you're a father. Indeed, that's the case. That polymer is used in children's nappies. So we go back to that polymer is used in children's nappies. I did give you a bit of a clue. So you can do this at home. Okay, kids, if you've got a smaller brother or sister, or indeed a grandma or a granddad who has nappies, you can take the nappy, you can open it up, you need to rip it open, and inside you'll find some cotton wool, which you now know is a natural polymer. And if you take that and just give it a shake, you see that dust falling? That's your polymer. Okay, so you can shake that over a piece of paper, collect the polymer, and you can do your own experiments with the sodium polyacrylate. So progression with polymers, with chemistry, it just needs one thing. You. That's all it needs. And I wanted just to finish on one point, that it was a great pleasure of mine yesterday to visit your university here in Nur Sultan. And in this building, I went to these chemistry labs and I met young scientists who were working on polymers. They are the next Wallace Carothers. They are the new innovators. And they're doing some fabulous work here in Nur Sultan. They're looking at making these LED units, these light-emitting diodes. They're making new conductive polymers, polymers that can conduct electricity and transform electric energy into light. And that is the future, ladies and gentlemen, which is happening here in Kazakhstan and is just waiting for all these young, intelligent individuals to put their own expression into that chemistry. I'd like to thank you for your attention. I'd like to thank Yerlan and all the others for all the invitation. And just to finish with, I'd like to show you some friends that I've now met. You saw Michael this morning, and also if you had the opportunity, you might have another opportunity again to see the magical performance of Pedro. So I'd like to say a big thank you to all of you, especially all of you here, Yerlan and Kazakhstan. Thank you very much.